But today in class, I would like to work on something else. I'd like to kind of work as a class on this. And and I kind of like it to be paper and pencil, believe it or not. So I'm going to give you let's see what I'm going to do to give you here. I'm just going to give you a function. We'll be working in three-dimensional space. And here is the function. F of x and y equals x squared plus 2y squared plus 3. I'll give you a rectangular domain so that the domain shouldn't be much of a problem. So x between 1 and 2. And I'd like the following items. I'd like you to parameterize the graph of f over this region. So parameterize the graph of f. So this could be like the top of a region if in three space, if there was one, but I just want to look at the graph. And then I want you to find u prime of that parameter, so u of that parameterization equals something. Let's say u of s and t. Then I want you to find u prime of s and t and the expansion contraction factor. For integrating. And then maybe use a little Mathematica to find the surface area, the area of the surface. And you'll probably want to use a little Mathematica to find the surface area. And let's begin with this. So I hope this is new old hat for you. And let's do this in about 5 minutes to get this at least set up. And you can set up this last integral, and if you have time, then actually find it. But the other stuff you can do by hand. Meredith, you're doing double duty today. We have two Merediths.
Yeah, my computer was having a kind of a heart attack, so I had to join on my phone until it got fixed.
Yeah, I figured it was something like that. Maybe stroke. Fortunately, my laptop's held up. I have a alternate, but it's not near as good as this guy. All right, let's take a look at this, see what we got. So the parameterization of the top is in 3 dimensions. So you got 3 variables. And since we have an X and a Y, this is in a function of X and Y, this is an easy parameterization, a graph parameterization, nothing tricky, where the 3rd variable is the function value, because you don't want to be on the bottom, you want to be up on the surface. The derivative is this, derivative with respect to S, derivative with respect to T. The expansion contraction factor is the sum of the squares of the maximal size determinants in here. So it's 1, 4t squared, 2 minus 2s squared. And this is the area integral. You integrate the 1 function, but you need the expansion contraction factor, ds dt. And what do you get for this? Did anybody actually get a value?
Do you want the exact number or the decimal approximation?
Just a decimal approximation, maybe a couple decimal places.
Oh, I think I got 49.9624.
49.96, almost 50. Everybody have any questions about this? We good? All right, a couple other things. Let's take a point in the domain, say the point 0, 2, and find the tangent plane, an equation for the tangent plane at, so when S is 0 and T is 2. Find the tangent plane when S is 0 and T is 2 for this parameterization. I should have maybe had you raise a hand when you've gotten this. Anybody gotten this so far? Well, let's take a look. Let's take a look. Did anybody get it? This is stuff from early in the course, but probably one thing that should have come into your mind was, why the heck does Humke want this? No, was what do I need in order to get an equation for the tangent plane? What do I need? And so in general, you are going to need a point on. So this is something that in general you will need. And you don't exactly have that yet. But then you need something else. If it was the Cartesian form, you would need a normal vector. Or you could go with a point and the slope at that time. And so if we have the point, then all we would need is the slope or a normal vector. They are all equivalent. Or if it's parametric form, we would need two directions. So these are kind of alternatives. Either one would work, and let's do them both. For the directions, the two directions are the partial derivatives. The partial derivatives give you the two directions. Here's the first, 1, 0, 2s, that's a formula for it. Here's the second one, 0, 1, 4t. These two vectors are where you use the variables one at a time. This is a derivative with respect to s. It gives you a direction. Derivative with respect to t, it gives you another direction. If these two are 0 or equal, then it's trouble, but here they're not. The point on, I gave you the 0 and the t, but this is the description of the object, the range of this function. So you got to plug those two in to get the point on. So the point on is 0, 2, and then 8, 11. 0 to 11. We good with this? And then for the two directions, they come from this derivative. So 1, 0, 2s, and the s was 0. So 1, 0, 0. The x-axis is the direction. Direction 2 is 0, 1. And then 4t, t is 2, so 0, 1, 8. The slope in the x direction is 0, rise over run. The slope in the y direction is 8. And so the slope in this case is the derivative of the equation with respect to s, 2s, the derivative with respect to t, 4t. And so there is the there are the two slopes, 2s, 4t. Slope in the x direction, slope in the y direction. M sub x, m sub t. So in our case, 0, 8. And then
So you're just looking at the z part to find the slope?
to find the slopes, yeah, the slopes are just found. That's what the partial derivatives mean. The partial derivative with respect to s, or with respect to x, the way I gave it, but with respect to s here, the partial derivative with respect to x gives the slope in the x direction. The partial derivative of the function with respect to y gives the slope in the y direction. So we haven't done that for a long time, but that's what these two guys are. Sarah, was this you asking me this? No, I know. Are we good with this so far? Pardon?
Could you remind me, how would you write the formulas differently when like writing the equation of the tangent plane?
Yeah, I'm gonna do that right now.
Sorry.
This is partial review for the final. I decided to do this as we go because it's needed in what I wanted to talk about today, and this isn't it yet. So we have two ways to go here. And so the first way I'm going to get parametrically, since I've got point on in two directions. So the parametric equation for the line I'm interested in is L of t, tangent line of t, equals the point on 0 to 11, plus t times 1, 0, 0, plus s times 0, 1, 8. Since it's a plane, a tangent plane, you require two directions. It's governed by two variables, L of s and t. It's not a tangent line, but a tangent plane. So you get two variables here, and this is its equation. S and t here are unrestricted in order to get the whole line. Lauren, we good with this one? And then I don't want to erase this stuff yet, but I guess I could. But the second one is the Cartesian equation. So part B is Cartesian. So it would be z minus 11, z naught, equals the slope in the x direction, which is 0 times x minus 0, plus the slope in the y direction, 8 times y minus 2. So using the x and y, here's the point slope form of this plane. Lauren, we good with this? Everybody
Yes,
else, we good with this? There's one more thing maybe we should find. I mean, there's the point normal form. And now we have the point on already, 0 to 11. So now we need the normal. And what is a normal vector to this guy? How do you find a normal vector?
The dot product is 0.
Yeah, that is true. If the dot product is 0, it is a normal. So
You
but
cross the two
if
directions.
you want the normal to the whole plane, it's more difficult than that.
Then
because
you
want-
cross the two directions.
Yeah, a cross
Yeah, you can
product.
take the cross product.
Yeah, a cross product is what does that for you. So you want to look at the cross product of 1, 0, 0, cross product with 0, 1, 8. Now what do you get here? Somebody help me out.
You get 0, -8, 1.
0 minus 8, 1. And so I guess I'm going to erase some of this stuff here. 0 to 11, I have to remember. So then that would be this form, x minus 0, y minus 2, z minus 8, dot product with, now here's where we use what Lauren said. We're going to use the fact that the dot product is 0. And with 0 minus 8, 1. So there is the point normal form. Everybody with me here? So if you are not, this would be a grand time to say, I have no idea what you are doing, Humpty. Or just say, could you explain that just a little clearer? Or something like that. Are we good? All right. If I should maybe give you more time, but if we're good, we're going to do a little bit more with this. So the next thing I'd like to add to the list here is a formula for the normal vector when sort of at an arbitrary point S and T inside the domain that I gave you. Where by the domain, I mean this. So find a formula for this normal vector to the surface. And not just 0, 2, but any point. What is a formula for it? Anybody get this? Here's what you get.
Negative 2s, comma, negative 4t, comma, 1, all multiplied by any constant.
Okay, but I just wanted any normal vector. Yeah, but let's look at this one first. How'd you get this?
I took the derivative with respect to each of the variables, and I took the cross product.
Yeah. Yeah, so these are the two columns of your derivative here. And you want to take the cross product of those, and that's exactly the idea. These are two directions at any given point, S, when S, and these are not on the graph, these are functions of S and T, so they're defined in the domain, but those are two directions. And if you take any two linearly independent directions and take their cross product, it'll give you a normal. And if you take this cross product, which you can do by hand, or you could use the machine if you want, but all of this can be done by hand. I is the first coordinate, gets multiplied by minus 2s. And then the j is negative, and it'll be 4t. And then the k is 1. So this is just a direct computation. Are we good with this? All right.
Wait, so you just took the cross product of what two vectors? I just can't see up there.
So the two vectors are the directions of the tangent plane. There is one, and here is the other. They are the columns of the derivative. Wait, Meredith, was this you that asked me? No.
Yeah, that makes sense.
Are we good? Are we good? Okay. So now I would like a temperature function. So I'm going to make up some temperature function in 3 space. So this will be a real valued function. I'll call it temp. So temp will map 3 dimensions into 1 dimension. It's a real valued function. It's not a force field. It's just a real valued function. So this temperature function will be a function of x, y, z, since it starts out in R3. And I'll make it x, y squared plus z, just something. And so the next thing I'd like you to do is to find the average temp over the surface, S. S equals the surface that we're talking about. The graph of that function over that region, that's S. So I'd like to find the average temperature over S. This should be pretty quick now. All right, let's take a look at this. So this is to get the average temp. You integrate the temp, find out how much is there. Well, we already did that. That's a surface area of 49.96. So we just have to integrate the temp. Integrate the temp the same way you do this, replacing 1 by the temperature function. And you shouldn't be using x, y's, and z's. You should be using s, t, and the z value, s plus 2t squared plus 3. So this is the integral, -1 to 2, 1 to 3. And plugging this in, you would get the x value, which is s, times the t value squared, plus s squared plus 2t squared plus 3. And now I'm missing something. There's something over here on the sideboard. What should be there? So this is temperature of S and T, so that works out. But what am I missing? Something is missing here.
The expansion contraction factor.
Expansion contraction factor, because you're using variable, you're using S and T variables, or you parameterize the thing. So you need the square root, the expansion contraction factor here. And if you integrate that, it should just pop out the value. And what do you get? Anybody do that? You want to use You could use just plain old integrate, but I would use n integrate here. I don't think there are any issues with this. Did anybody get it? Is this a problem? What happened here? Lily, what happened?
I'm currently waiting for my Mathematica to do it.
Oh. Did you use n integrate here or just integrate? It'll take a long
I had used
time.
the integrate symbols, so I'm currently putting in n integrate. Oh, I actually just finished.
Okay. So
Um,
n integrate is infinitely faster than integrate for all of these, but what do you get?
I got 16.4933.
For just the numerator?
No, for both.
What did you get for just the numerator?
I did all of it at once, so
Oh.
I do not know.
Did anybody just do the numerator?
You get
It's really fuzzy. Can I ask you? So you substituted in S and T for X and Y and temperature, but what did you do for Z? I just can't read.
The z value. The z value,
Oh, of the function. Okay.
which is the function in this case, right? We have an x, a y,
thank you.
and a z, so
It's just blurry and I couldn't see.
The numerator is 824
824
and some change. Yeah.
and some change. Okay. And so if you divide 824 by 50, it should give it to you. And so that's it. So that is the average temperature. And now what we'd like to do is to, I'm going to give you a vector field now. And this vector field is going to be defined on all of three-dimensional space. I think I have one picked out here. So this vector field is this, xy squared, comma, minus yz, and then x squared plus z squared. So this is a vector field on all of three-dimensional space. And I would first of all like to look at this vector field. Plot the vector field.
Could you read one more time what the vector field is?
Xy squared minus yz, x squared plus z squared.
Thank you.
Maybe can you look at speaker view while I look at gallery view or not? So if you are not on speaker view, you should be on speaker view. Then unfortunately, every time I talk, I'll be on, but you'll be able to see things better. The views are in the upper right-hand corner of the screen. So Noah, what are you using to plot this vector field? What command?
My Mathematica has actually been struggling, so I haven't been able to pull it up.
Oh,
My
oh.
computer is making a lot of fan noises right now, so.
We got it working hard. Let's see, Dan, did you get this one? What did you use to plot it?
Not yet. I'm trying to find something.
So this is to plot these vector fields. There's always the one command to use. Can anybody help me out here?
Vector plot.
Vector
3D.
plot or vector plot 3D?
Vector plot 3D. Yep, vector plot 3D. And then you put in this, and then you put in a restriction for X, Y, and Z, and that's it. So we're going to keep this up here. I'm going to keep the original function. And the formula for n. So here you want vector plots 3D. And then the xy squared minus yz, x squared plus z squared. And then you'll need x running between, I don't know, minus 10 and 10 or minus 2 and 2, y between minus 2 and 2. But you should include this domain. This domain should be included in what you do. In fact, you could make the domain equal to that, minus 1 to 2, y being 1 to 3, and then fool around with z plots to make sure you incorporate kind of the maximum and minimum of the function, so you incorporate the whole plot. So this is a vector field, a force field, and I didn't ask you to plot the graph, but the graph lies inside that force field. So points on the graph, points on the surface are being affected by the force field. And we would like to find the integral of the force. Now you can't exactly do it along the graph, because along a surface, if you have any surface, even a plane surface, any point, there isn't a particular direction that you're going. The plane has multiple directions. So you can't find the force kind of that's along the plane. It doesn't exactly make sense. Force along things is a line. But you can do the force across it, because a normal, that would mean finding the force in the normal direction, and the normal we can find. So we would like to find the force across this surface. We can find the force along lines, but we would like to find the force across S. And we would like to integrate the force across S. So just like we did with lines in one dimension, you can find the integral of the force across a curve. Here we can find the force across a surface. And the force across the surface, I'm going to put my function up here so I can erase this part. So f of x, y, z, just so I remember, is xy squared minus yz x squared plus z squared. So the force across S is the integral over S of the force, that's F dot n, and it's dot a unit vector in this direction. So this n is not a unit vector, so we'll have to divide by it. And then we have to multiply by the expansion contraction factor. maybe I did too much at once. Maybe just f dot n over the surface. And then this is equal to the integral -1 to 2, 1 to 3, f dot our parameterization u of s and t dot a unit normal vector times the expansion contraction factor ds dt. And the one thing, I would actually like to compute this time, but the one thing I'd like us to see is the expansion contraction factor is exactly the same as the length of this vector that Peirce found for us. This length of the vector that Peirce found is the square root of 4s squared plus 16t squared plus 1. That's exactly our expansion contraction factor. So just like in line integrals, these two divide. And so this ends up to be, if I can just erase this, the integral of the force field on the surface. The force field on the surface means you substitute the formula for the surface, that's the parameterization, substitute that in, find the force of it. Force field is a vector field, so that'll be a bunch of vectors. Dot product that with -2s minus 4t1, and it gives you the force across the surface. And this thing has a name, and this is called flux. So this is the flux of F across S. And Menards sells flux. If you go in and ask Menards for flux, they'll sell it to you. I mean, a lot of people know about this stuff. So let's go ahead and take a look at this computation here. We've got our formula for N. We know what F is. We know what U is. We know everything here. We can just compute it. So I'm going to erase this stuff and just compute this flux integral. So integral 1 to 3, integral -1 to 2. And the first thing to do is f of u of s and t. But f is in terms of x, y, and z. This is kind of what Meredith asked me a little while ago. What is the x? What is the y? They are the values that you have. Here's your x, here's your y, and here's your z. They're restricted because they're restricted to being on S. And this is what it means to be on S, this formula. The range of this formula is S. And so when I plug those in, I will get the x value, which is S, times y squared, so that's times t squared, and then comma, minus y, so that's minus t, times z. Z is s squared plus 2t squared plus 3, comma, x squared, x is s, so that's s squared, plus z squared, and z is s squared plus 2t squared plus 3 squared. That is the force field on the surface. And now we have to dot that with the normal, not the unit normal, but this normal, this particular normal, minus 2s minus 4t1. And that's a dot product ds dt. So I'm going to do a little bit more pencil and paper, but I actually want to compute this. So the dot product, first times the first, so I get minus 2s squared t squared. Then it'll be plus 4t times this thing, so plus 4t squared. times s squared plus 2t squared plus 3. And then plus 1 times this guy here, which is s squared plus the quantity s squared plus 2t squared plus 3 squared ds dt. I wouldn't simplify anymore. You could have Mathematica simplify if you want, but this is what we need to integrate. -1 to 2 in the s direction, 1 to 3 in the t direction. This gives us a measure of the force due to this vector field across this surface. Now you might say, where is this stuff possibly applied? It actually is applied everywhere in physics, but it's also a critical value in financial mathematics, in higher level understanding of markets. It is critically important in understanding osmosis and movement of material across cell boundaries. This flux is used a lot. It's non-trivial. So you can't just, not everybody can just sit down and do it. It takes a lot of work to do these things. A lot of data needs to be collected. So combinations of a lot of statistics and a lot of estimation and a lot of understanding of what you are finding when you find integrals of force fields across surfaces. Hopefully before the hour is out, we will get an answer to this. None of these are particularly simple. This is not so simple.
I got 2,631.6. I know someone else can confirm that.
2,631.6.
Yes.
Is this correct? I have absolutely no idea. I didn't do this, but because of the amount of complication that's involved here, these answers need to be checked a lot. We're into recounts now, and these values always need to be recounted over and over and over, redone to make sure they're correct. If they're not, and you're sending a spaceship to Mars, they're not. Just one little miscalculation can send your spaceship off to Pluto or crash into Mars or whatever. You think this hasn't happened? This has happened. So friends of mine at JPL, Jet Propulsion Laboratory in Los Angeles, were involved with a Mars crash. Actually, their error was even worse than this, but these things are used a lot. So this is the flux integral, and we have been doing fluxes in 2 dimensions. This is the second form of Green's theorem that I gave you, and we've been finding flux integrals across curves in 2 dimensions. Those are also important, but in 3 dimensions is where you see a lot of important applications of this. So these are next time I think will be the last piece of new material that I'll give you for the course. And then on Friday, we'll talk about that and problems. On Tuesday, we'll talk a little bit about the whole course and stuff. The first part of this problem, by the way, actually almost this whole problem came from a final exam I gave several years ago. So, and this is the kind of integrated exam question that I like and I give a lot of. So I give you a single formula. In this case, I gave you a surface. I had you parameterize that surface. You had to find the derivative of that parameterization. You had to do some stuff with the derivative. In this case, find plane tangent to the surface. You had to find the average temperature. So you had to deal with a real valued function, and you had to find the flux. So I recorded this. I'll stop the recording now, but I recorded this, so I'll put this up